So I'm doing this after a long time, but it's on student demand. So I am excited. Here I am with complex numbers. Hello everyone. So before we begin with complex numbers, I just need to talk about a little bit of background. So you might have studied square roots back in the day, and when you come across something like square root of minus 36, which is not a real number, that's how our teachers have told us, then the question is, then what is it if it's not real? So in 11th grade for the first time, we come across this notation I, which is under root of minus 1. And it was formalized by the great mathematician, one of the greatest of all time, Leonard Euler. And then starts the entire theory of complex numbers, which by the way begins with positive powers and negative powers of I. So to describe complex numbers, we need to describe I first. And how this I is used, you can see it through an example here. So suppose I need something like under root of minus 36. I can describe it as 36 into minus 1. And then you can express this under root of 36 as plus minus 6. And then write under root of minus 1 as I. So this turns up as plus minus 6i. And then I can formalize it and describe higher powers of I. So you can have positive powers, you can have negative powers, and you can see the lookup table of I that I have mentioned here. So if you just have I, well, it's under root of minus 1. But what if I square both sides and I find I square? Then I square is going to be minus 1. Just remove the square root. If I need I cube, then it's going to be I square into I, which is minus 1 into I, that's minus I. And if I need I to the power 4, well, that's going to be I square into I square. You know that I square is minus 1, so minus 1 times minus 1, you end up as getting the answer as 1. So that's why these are the 4 results that you should know. And then comes the question, what happens if I consider negative powers of I? So let me just remove this from here and talk about the negative powers. So now I need I to the power minus 1. As a rule, we don't have to keep I in the denominator. So if I want to write I to the power minus 1, well, basically it's 1 by I. But as a rule, this I shouldn't be in the denominator. So I'll multiply to numerator and denominator by I so that the denominator I is removed. I get this as I upon I square. Now you know I square is minus 1. So I upon minus 1 is just minus I. Now if I need I to the power minus 2, well, the idea is simple. You just write it as 1 by I square. As I square is minus 1, this becomes 1 upon minus 1. That's minus 1. So that's quite easy. What happens if you have I to the power minus 3? Well, I to the power minus 3 is 1 by I cube. And then you just multiply to numerator and denominator by I. And you will get this as I upon I to the power 4. Well, I to the power 4 is 1. That's why this is I. And what happens if you try to find I to the power minus 4? Well, this is 1 upon I to the power 4. As you know, that's 1. That's why I to the power minus 4 is 1. Now, there is something that you should look at. And this is just a basic observation. And the first thing that comes to my mind is for I square and I to the power minus 2, the result is the same. And for I to the power 4 and I to the power minus 4, you again get the same result. So I can make a conclusion that if the power is even, it doesn't matter if it's a negative power or a positive power, you get the same answer. So I to the power 6 and I to the power minus 6 will be same. I to the power 8, I to the power minus 8 will be same, and so on. And then if you go on and think about it, if the power is odd, well, I is under root of minus 1, so I is just I. And because of that, if you just think about odd powers, well, then if you apply a negative power, then your result changes by negative sign. So what I'm trying to say is I to the power 1 is I, but I to the power minus 1 would be minus I because the result changes by minus sign. And then if I talk about I to the power 3, well, I to the power 3 is minus I. But I to the power minus 3, again you are applying a negative power in odd power, then the result would be a positive value, just the opposite sign value. So now the question is, what happens for higher powers of I? So what if you want to find something like I to the power 10? Well, can you get that? The easy answer would be yes, but you'll have to work it out. And then there comes this method as prescribed by state or CBSE board that you should express it as I to the power 4 times I to the power 4 times I square. Just write it in powers of 4, something like that. And then write it as 1. This is 1. This is minus 1. So the end result is minus 1. But for me, this method, even if, it's quite intuitive, still I would suggest you another method which is quite good. And that method would be this one. For higher powers of I, all you need to do is divide the power by 4. So whatever you're asked, like I to the power 14, divide that by 4. And then in step 2, you just find the remainder. If that remainder is r, then just express I to the power n as I to the power r. Use the lookup table in the third step to get the final answer. So this is the lookup table that we have already discussed, and this is the procedure to find higher powers of I. Again, let's put that to use. So if you want I to the power 14, divide this power by 4. If you divide it by 4, the remainder is 2. That's why this is I square, and I square is minus 1. So you can get the answer pretty easily. Suppose I write something like I to the power 135. Now again, I know that 120, 124, 128, 132. So divisibility goes till 132 for 4. And then I'll get the remainder as 3. So I'll write I cube, which is minus I. So this is quite fast if you want to find I to the power minus 98, something like that. Then I know that it's divisible till 90, then 93, 96, 96. Yeah, so I'll get it as I to the power minus 2. But it doesn't matter for even numbers if the power is, say, positive or negative. You end up with 1 upon minus 1. That's minus 1. So this method is possible, easily usable for negative as well as for positive numbers. And let's take up one last. If you want something like I to the power minus 138, something like that, you should divide the power by 4. So that's I think the remainder would be 2, is it? Yeah, I to the power minus 2. You end up with minus 1 as your answer. So again, have a look at this, and we'll move on to what basically complex numbers is. So the idea of complex number is that if you have a real number and you combine that with an imaginary number, so take a real number A and combine it with imaginary number Bi, then the entire idea becomes complex in nature because you have something that exists with something that doesn't exist. That idea is complex in nature, and that's why the name is complex number. So complex number is of the form A plus Bi. It's always denoted by the letter Z, and you should know that the real part of Z denoted by Ra of Z is A, and the imaginary part of Z is B and not Bi, because Bi is the imaginary number, B is the imaginary part. Okay, and if I want to describe a complex number, you can take a basic example like 3 plus 4i, where 3 is the real part of z and the imaginary part of z is 4. Okay. Now think about this for a second. So you have something that exists and something that doesn't exist, and you combine them up and you form the complex number. But what basically complex number is, like how to interpret that? So you can take the example of the real x-axis and imaginary y-axis. So it's like a Cartesian coordinate system, but with a slight modification that there is real x-axis and an imaginary y-axis. It's called as the Argand's plane. And in that plane I can mark any complex number using the method that I have described here. So if I want to describe the complex number a plus bi, I must mark distance a on real x-axis, distance b on imaginary y-axis, and then if I take the resultant, I would always end up with the complex number a plus bi. So that's quite a fascinating thing, that complex numbers are basically points on a 2D plane. So whatever geometrical application of point is present could be applicable to complex numbers in general. And now if I want to mark a complex number like say 3 plus 4i, that's the example that we have taken. So we'll mark a distance of 3 on real x-axis and then a distance of 4 on imaginary y-axis and then take the resultant. So that's going to be our complex number 3 plus 4i. Alright, so that's the end of the first module here, and I'll be back with the second one really soon. So see you all. Thanks.